Okay, so here in chapter 6, we're going to start looking at systems of linear equations and systems of inequalities. Okay, um, so we'll get into a little bit more about what a system is in just a minute, but just look at our objectives. We're going to be solving systems of linear equations, and we'll graph some, and we'll use a substitution and elimination method. So basically, though, we're trying to solve a system of linear equations, and we'll solve systems of linear inequalities. So those are our goals, to find out what a system of linear equations is, and then in chapter 6 we're going to be solving them using a lot of different methods. All right, so let's jump in here with 6.1. Specifically, today we want to look at graphing systems of equations. And again, you don't know what a system of equations is yet, maybe, but we'll get there. So our objectives for this first part of the chapter is to determine the number of solutions that a system has, right? We want to know how many answers we're looking for. We'll want to know what that answer looks like, but we'll want to know how many to look for. And then once we can determine how many solutions the system has, we'll look at the first method of solving systems of linear equations, and that will be by graphing. So we'll go back and we'll talk about things like y equals mx plus b, where we need to know a slope and we need to know an intercept. And this is one of the ways that we graph equations. There are other ways that we graph linear equations. This is one of them. Okay, so excuse me. So what is a system of linear equations? A system of linear equations, it consists of two or more linear equations. So in other words, we have a linear equation. We have a line, right? We remember what a linear equation is. And a system simply says that we have two or more of them, okay? Such as this system here, right? Y equals 4x plus 1500, y equals 10x. That's two different equations, two sets of x's, two sets of y's. They're lines independent of each other, but when we group them together like this, this is a system of equations. All right, now here's what a system would look like when we graph it. Right, we recognize that there is a slope of 4 and an intercept of 1500. We recognize that our second line has a slope of 10 and there is no intercept. Okay, and so this is what that would look like. And I've jumped to the punchline on this first one because I wanted you to see a system of linear equations and then just kind of generally see what happens here. This is what we're going to be doing. We're going to be taking a coordinate plane and putting two or more equations on there, and then kind of observing to see what happens, right? So 4x plus 1500, we see an intercept of 1500, and we're not really able to, on this scale, count off a slope of 4 over 1, but we can kind of see that that is a slope of probably 4 over 1, okay? And intercept is 0 and a slope of 10, okay? So we can see that that's a steeper slope, okay? And so that's what happens. We have two lines that get graphed, and then hopefully what happens is they intersect somewhere. Okay, that intersection is the solution. Okay, the solution of the system is the ordered pair or pairs. It could be more than one, but the solution is the ordered pair that satisfies both equations. In other words, it's where those two lines intersect. Where do those two lines come together? That point, whatever x is and y is true for both of these equations, and so therefore it is the solution to that system. Okay, now the number of solutions that we can have. Okay, so we'll talk about the number of solutions. We'll talk about the terminology that we'll want to try to use when talking about those solutions, and then I want you to see what the graph looks like of the different ways and numbers of solutions. So we've looked at one like this already, and we have two lines. And those two lines intersect in exactly one place. And so there is exactly one solution. Exactly one solution. This type of system is consistent and independent. Consistent and independent. Yes, you'll need to know that terminology. Consistent because it has a solution. independent because those lines are, oh, that was really bad. My apologies. Independent because the lines are independent of each other. You'll see what I mean when we look at the next one. Excuse me, the next two. Right, so an infinite number of solutions. Now, do you see the second line here? You don't, because it's one line on top of another line. So sometimes we'll see a system that is a line on top of another line, right? And so that system would have an infinite number of solutions because every point on one line is on the other line as well. Now that system, it still has an answer, so it's still considered a consistent system. And this time though, it's going to be consistent and dependent because one line depends on the other one, and so it's a dependent system. These lines are independent of one another. They're separate. So it has an answer, it's consistent. Has an answer, it's consistent. Independent because the lines are independent of one another. Dependent because one line is dependent on the other one. They're on top of one another. So exactly one solution and infinite solutions. Okay, so the other thing we would be looking for is when is there no solution? And so there we go, no solution. And no solution systems are inconsistent because there is no answer. They are inconsistent. This system doesn't work, in other words. Notice that these lines don't touch each other. And if you'll remember that back, that means that those two lines have the same slope. So lines that have the same slope, but if they don't intersect, those are going to be your no solution type situation. So here we go. Let's talk about this. Here are the three things we've talked about already: consistent, independent, one answer; consistent, dependent, infinite answers; inconsistent, no answers, no solution. Okay, so here are two equations: y equals negative 2x plus 3 and y equals x minus 5. If we were to graph those, there they are. Okay, intercept of a positive 3, intercept of a positive 3, slope of negative 2, negative 2 over 1. Okay, so there's that line. Y equals x minus 5, so negative 5 is my intercept, plus 1 is my slope. Okay, and so these are those two lines, and the question is, do they have an answer and how many? Okay, these lines intersect at one point, so it is consistent. There is an answer. The lines are independent of each other, and so this is a consistent, independent system, and it has one answer. Okay, let's look at another one. Again, same three options here for solutions. Y equals negative 2x plus 1, y equals negative 2x minus 5. Now, one thing we want to notice here right off the bat is they have the same slope. Okay, same slope. These are the special cases. They're either going to be the exact same line, or they're going to be parallel lines that don't cross the y-axis at the same place. So here we go. One intercept is at a positive 1. One intercept is at a positive 1. One intercept is at negative 5. But they have the same slope. Okay? And so this system is inconsistent. These two lines are never going to touch. Okay? One more. Again, same three options. Here's our system. Intercept of positive 1 for both of them. Slope of negative 2, slope of positive 1. Could we graph those two equations? We could. Both of them have an intercept of positive 1, slope of negative 2. So we know where that line is. Slope of positive 1. So we know where that line is. Do they intersect? Yes. At exactly one place. And so this is a consistent, independent system again. One thing I want to go and throw out here before we look at the next thing, we talked about that a solution was the point, the ordered pair that worked for both of these equations. I want you to notice that these two lines intersect at this point right here, if you can see that, where x equals 0 and y equals 1. And so that is our solution. If we were to come over here and plug in x is 0, y is 1 to both of these equations, it would be true. And because it's true, it's the solution to this system. Okay. All right. So that's one of the things that we're going to want to be able to do is identify what that point is. Okay. So let's jump in here. Graph the system of equations to determine the solution. Now, one of the things you'll notice here is that these two equations are not in slope-intercept form, and so one of the difficulties that we'll have sometimes is we'll need to take the steps required to get the equations into slope-intercept form to be able to graph them, if that's how we're going to graph them with slope-intercept. And so let me take a second here, and we're going to right here we'll add y to both sides, and so x equals 2 plus y, and then we're going to subtract 2 from both sides, and so y equals x minus 2, and that's one of our equations. That's one of our equations. Intercept is -2, slope is a 1 over 1, and so we're going to edge graph as much of this line as we can. Okay, so there it is. We'll connect all these dots here. And so that's one of my lines. Okay, we're going to take the other one and we'll do the same thing. We will, let's get the y by itself. We'll do that by subtracting 2x from both sides. And then we'll divide both sides by 3. Okay, and so we have an intercept of a positive 3. And we have a slope of -2/3. And interestingly enough, that first point that we got to lay down actually is going to end up being our solution. Okay, so this is a consistent, independent system with x is 3, y is 1 as our solution, because that's where the two lines intersect. And again, we can plug in 3 and 1 into our two equations, and we can check, and it's going to work. Okay, 3 minus 1 is 2. 9. Let's see, 3 plus 6 is 9. Okay, so both of those equations work with that point. All right, let's do one for you, and I think I made it a little easier for you. One of those equations is already in slope-intercept form. So your job is to take the other equation and put it in slope-intercept form, and then find your solution. And so that's your job. Determine the solution. Tell me what the ordered pair is that is the solution for this system, right? And remember, there could be one answer, there could be an infinite number of answers, or there could be no solution. You are determining the solution. So is there a solution? How many? And if so, what is it? All right, go. Okay, so the first line you should have been able to graph immediately. Intercept of -3, slope of -2. Okay, that one graphs pretty quick and easy because it's already in the right form. The other one you had to do a little work with. It's going to be important to graph cleanly. Sorry about that. Okay, so let's subtract 6x for both sides. Let's divide both sides by 3. And what do you notice there? Y equals -2x minus 3. Seems like it's the exact same line. So, consistent, and I'm not spelling that right, I apologize. Consistent, we'll stop right there. Consistent, dependent, and an infinite number of solutions. Okay, so that's your solution, infinite. All right, let's try one more. I'll give you one that actually maybe sort of kind of works out. We'll see what happens. All right, this one's yours. Both of these equations have to be put into slope-intercept form to graph them. So, all right, welcome back. So, in solving those two equations, the first equation would have given you y equals 2x plus 1. And So positive 1, slope of 2. Okay, we'll get as many points as we can. Connect the dots. Okay, change colors here. Solving the second one, you would have gotten y equals 2x minus 3. Look at that. Same slope again. So this is one of your special cases. This time we have an intercept of -3, but the slope of 2 means that these two lines never get any closer than they were right there. And so this one is an inconsistent system. Inconsistent. And there is no solution. Okay.